My remote has been troubling me for quite some time, and fixing a problem like this where the screws have gone inside is a little difficult. But I have a solution. With tools like a screwdriver, it becomes easy for me to fix problems like these. Oh, by the way, I forgot to tell you. Hi, I am Raj, and today we will learn an interesting topic on moment of a force. Students, before going to the concept in depth, let us see how a force causes a body to turn around a fixed body. Already we have learnt that when a force is applied on a rigid body, it produces linear motion.
See here carefully. The boy winding his wristwatch. What did you observe here? The boy applies force at a fixed point on the rigid body, and the same force causes a turning effect about that fixed point. This force is nothing but moment of a force. So, we can define it as a force which is applied on a rigid body, fixed at a point, that produces a turning effect and is called moment of a force or torque.
Let us apply this moment of force or torque on this door for our better understanding.
When we push the door at its outermost edge, that is at the handle, the door rotates about the hinge. In performing this act, we applied a force at a distance perpendicular from the hinge of the door. Watch what happens when we try to push the door at a shorter distance from the hinge. We have to apply more force to close the door. So, when we move closer to the hinge, we have to apply greater force to close the door.
We can observe 4 things from the activity that we did above.
To produce a rotation about a fixed point, the body needs to be rigid. The body should be free to move about a fixed point. The point of application is far away from the fixed point. The force applied is perpendicular to the line joining the fixed point and the point of application of the force. We can also define the moment of a force as the product of the magnitude of the force and the perpendicular distance from the point of application of the force to the fixed point in the body. Mathematically, we can say moment of force is equal to force multiplied by the perpendicular distance, or m is equal to F multiplied by d. The unit of moment of a force under SI system is Newton meter or Nm, and under CGS system is dyne centimeter.
Remember, moment is a vector quantity. Now, let us see the principle of moments.
For a rigid body in equilibrium under the action of forces in a plane, the sum of the clockwise, that is negative moments, about any point is equal to the sum of anti-clockwise, that is positive moments. We can also define the principle of moments as the algebraic sum of the moments of forces about any point in that plane to be equal to 0.
Let us verify the principle of moment with an example.
Take a metric scale, 2 loops of thread, a wedge, a hanger weight and a spring balance. Support the meter scale with its center on a wedge. On one side of the scale, attach a loop of thread and suspend the hanger weight. On the other side, attach another loop of thread and attach a spring balance. Pull the spring balance to bring the scale to horizontal position. Spring balance reading shows the weight required at that point to counterbalance the weight on the other side. Note the values. Distance of the hanger weight from the center, S1 is equal to 20 centimeters. Distance of the spring balance from the center, S2, is 40 centimeters. Hanger weight on the side left, that is anti-clockwise positive movement, is equal to W1, which is equal to 100 grams. Spring balance reading on the other side, that is the right side, clockwise negative moment, that is W2, is equal to 50 grams.
Now, let us find the weight of the body by the principle of moments by an experiment.
Take a meter scale. Suspend it from a stand by means of a loop of thread, its center. Suspend the body, whose weight is to be found out, by means of a loop of thread on the side of the meter scale. Take a known hanger weight and suspend it on the other side of the meter scale. Now, by adjusting the distance on either side, bring the scale to horizontal position. Note the lengths according to the principle of moments. Effort into effort arm is equal to load into load arm. That is, capital W1 multiplied by D1 is equal to capital W2 multiplied by D2. We know W1, D1 and D2. We can find out W2 using the equation W2 is equal to W1 multiplied by D1 whole divided by D2.
Let us demonstrate an activity that most of us do in our daily lives. When we open or close a tab, we have to use a thumb and a finger. If we try to open or close the tab with one finger, we find it is very difficult to do so. In the above activity, we note that we have applied two forces that are equal in magnitude, but in the opposite direction to open the tab. Such pair of forces which are equal in magnitude, unlike and parallel to each other when act on a rigid body at different points to produce a turning effect in the same direction is called a couple. The perpendicular distance between the parallel lines along which the forces act is called the arm of the couple. So, the moment of the couple is equal to the force multiplied by the length of the arm. Now, let us see what are the moments of a couple. First, moment of a couple tends to produce pure rotation, and whenever a body undergoes angular acceleration, a couple is acting on it. Second, the moment of a couple is the same about any point in the plane of the lines of action of the forces and is measured by the product. Third, a couple can never be replaced by a single force. That is, it can be replaced by any other couple of the same moment. Fourth, the resultant of a set of two or more couples is a couple of moments equal to the sum of the moments of the individual couples. Let me show you more examples from the daily activities that we perform. Look at the man winding a watch, a lady churning butter, a man winding a clock, a boy sharpening a pencil. All these activities make use of couple. Next, let me show an application of the principle of moments.
This technique was used in the steelyards in Roman times. The steelyard is a balance with unequal arms and a fixed fulcrum. It consists of a beam pivoted on a knife edge and a slider that moves along a calibrated bar. The beam remains horizontal when no load is placed on the pan and the rider is at O. When a load is kept on the pan, the rider is moved till the beam becomes horizontal. The position of the rider on the bar is the distance from the fulcrum. The weight is calculated by taking the moments of weight to be measured and the rider about the fulcrum. S multiplied by CO is equal to W multiplied by CG, where S is the weight of the rider, CO is the distance of the fulcrum from the rider, and O is the zero reading on the scale. W is the weight of the beam and CG is the distance of the center of gravity of the beam to the fulcrum. If load L is attached to the pan and rider S is placed at position X to balance the weight by the principle of moments, we get L multiplied by CA is equal to S multiplied by OX, or L is equal to S multiplied by OX divided by CA. Thus, L is proportional to the distance of S from O. The scale marked on that bar enables the weight of the object to be read off directly.